Hi everybody. So last video we talked all about means and averages, okay, and measures of central tendency as well as medians and modes. Okay. Well, we're going to see a mean can help us tell us a lot about a data set or a population, but it needs to be so in the context of other things and other factors. And let me just give you an example here. So here we have a data set with 50 entries. The minimum value is 0, and the maximum value is 10, and the mean is 5, and the median is also 5. So the question is, some things I'd like you to think about. How many entries do you think are equal to 5? And how many entries do you think are between 3 and 7, let's say? And one other thing, how many entries do you think are between 1 and 9? All right. Well, it turns out that the answer to all those questions is 0, because this is what our data set looks like. They're all zeros. Half of them are zeros and half of them are 10s. Okay. They're about spread out as far apart as you can be. Obviously, it's they have two modes, right? 0 and 10. So this is an extreme example of a bimodal distribution. And the lesson here is it's not just the mean we need to take into account, but we also need to take into account the variation of these data values, how they're spread out, and not particularly the variation or the variance. And so that's what we're talking about today. Okay. So there are a few ways we can talk about measures of variation. That is how the data is distributed. Well, we already talked about the range of a data set, and that's just the maximum value minus the minimum value. That's okay. That doesn't tell us a whole lot by itself. A more interesting way would be to sort of take into account how far each data value is from the mean, and then some sort of average of that. Now, we define a derivation of a data entry x as just to be x minus mu or x minus x bar. Okay, when it's basically that value minus the mean. And let me remind you that the population mean and the sample mean, they're both calculated the same way. You both add up all the entries and then divide by the number of entries. But the population mean is a parameter, so we denote it by the Greek letter mu, and the sample mean is a statistic, so we denote it by x bar. So that's a derivation. It's either x minus mu or x minus x bar. Now, what we do, instead of adding up all the derivations and taking the average, we're going to do something a little different. We're going to square the derivations, then add them up, and then divide by, well, we're going to divide by either the population size, if we are in a population, and if we do that, that's the population variance. And that's denoted by sigma squared. Now, why do we call the variance sigma squared? Well, what is sigma? Sigma is the square root of the variance. So we take sigma to be the square root of the sum of the squares of all the derivations, and divide by the size of the population. And the reason we're going to make much more use out of the standard deviation than the variance. One reason is that the variances can be quite high, and the numbers can be quite high, and they might not be that helpful or easy to work with. But also is we have this idea of units. The data entries have units. The question is what happens when we square units. What are we really talking about? When we take the square root, we don't have that problem anymore. Okay, so it's really the population standard deviation that we'll be working with. Now, that's if we were working with a population. If our data set is a sample, then we have a sample variance, and that's calculated a little bit differently. The only difference is we divide by one less than the size of the data set, or the size of the sample. And then the sample standard deviation we denote by S as to be the square root of the sample variance. Okay. The reason for that is because we can't get into the reason right now, but it's going to make life a lot easier for us when we make use of the central limit theorem and do hypothesis testing. If you really want to see why we do this, I suggest you take Stat 276. But for now, we'll just take this as given right now. So obviously it means, what we need to do is we need to know if we're talking about a population or a sample. As you can see, these equations can be very the calculations can be very ugly, and we're going to do a couple of them by hand, but we're going to do most of these on our calculator. The question is, well, why don't we use this? Why don't we just take out all the averages of all the derivations? Is because they all cancel out. They will all cancel out, and if you compute this, for example, if we just take if we just have, let's say, three data sets, and we take we have x1 x1 minus mu plus x2 minus mu plus x3 minus mu, and then we add these up together, we get x1 plus x2 plus x3 minus 3 times mu. Okay, well, what is that going to be? This is the same thing as mu times 3, and this is 3 times mu. So this is just going to be 0, and in fact these sums will always be 0. Okay. All right. So because we're just remind ourselves, x1 plus x2 plus x3 divided by 3 is mu, and so you multiply by both sides by 3 and you get this. So, all right, so that's why we don't do that. Now, there's some people might ask, well, why don't you use absolute values? Well, there's another reason, and I think your book discusses it towards the end of this section. So let's just look at what we would have here for our data set. You can see that all these are going to be, all the derivations are either going to be plus 5 or minus 5, right? Because if we take 0 minus 5, we get negative 5, but if we square them, we get positive 25, right? And if we take 10 minus 5 squared, this will be 5 squared, that's 25, right? So if we take the sum of all these, there are 50 values, I equals 1 to 50 of xi minus mu. This is going to be sum from I equals 1 to 50 of xi. All of these are going, if we take the squares here rather, these are all going to be 25. So we're basically adding 25 to itself 50 times. So this is going to be 25 times 50, which is 1,250. And so sigma squared, the population variance, remember that our n is if we consider this as a population, the population size is 50. So sigma squared will be 1250 over 50, which is just going to be 25. And taking the square root, we just get 5. And that's not at all surprised, because all these entries are exactly 5 units from the mean. If we compute sigma squared, The sample variance, this is going to be 1250 divided by 49. And this would be a little bit bigger. This is 25.51. And then the sample standard deviation will be the square root of 25.51, which is approximately 5.05. Oh, okay. All right. Now, as I said, these are very extreme, but the standard deviations are very, very large in this case, as we can see. Give you another example. If we take the example 1, if we take the data set, we have only 15, we have 5 values in this case, but you can see that we have to, if we compute this out, if we wanted to find the sample standard deviation, well, first of all, we would have to take the mean. So let's find the mean. This would be 16 plus 17 plus 30 plus 44 plus 61 over 5. And this turns out to be 33.6. Okay. So well, actually, let's just compute the sigma, the standard deviation. So this would be 16 minus 33.6 squared plus 17 minus 33.6 squared plus 30 minus 33.6 squared plus 44 minus 33.6 squared, and we're running out of room, plus 61 minus 33.6 squared. Okay, all under the square root divided by in this case we have 5 units, so that would be 5. Okay. And when you compute this, this turns out to be 17.072. Okay. And you really don't want, you'd be glad we don't have to do this by hand, because we would, there would be, first of all, there could be a lot of round off error. The way some people use their calculators. Okay. But then if we wanted to find that, so that's the population standard deviation, and then the sample standard deviation would just be the same thing, 16 minus 33.6 squared, and so on. Over, instead of 5, we have 4. And this turns out to be 19.087. Okay. You don't want to do this, okay, by hand, really. So fortunately, our calculator will do it for us, because it knows how to compute these standard deviations. So right now, let's go back to our things with our example where we have our data set, where we have the number of weeks that students visited the library during a certain year. And let's see if we take I'll show you how to do this. So, turn this on here. Okay, so if we go back, go to Stat, Edit. You can see right here in column 5, we've done the same. I entered all these into our computer, into our calculator as before, and so we get cell 5. So we go back and hit Stat. We want to do a calculation, and we want it to be first variable stats. So we're on 1, first variable stats. We want to do that. Our data is in at column 5. Okay, now we already found out that the mean x bar is 25.142. The two standard deviations are down here. The sigma x stands the population standard deviation, so sigma would be 14.149 if we round this off. So round to 3 decimal places to be on the safe side. And then the sample standard deviation would be this 14.409. Okay. All right. So if we that's the this is the population standard deviation. This is the sample standard deviation. To find the variance, all you have to do is square these. So the variance, sigma squared, will be 14.149 squared. And it's usually a good idea to take a few more digits, maybe to ensure accuracy. But 14.149 squared is 200.194, and so this is the sample variance. And if we take the I take s squared, this will be 14.409 squared, and we can just do that. It's 14.409 squared. And we can see that's a little bit bigger. That's 207.620 if we round off. Okay. And that's our, actually, sorry, this is our sample variance, and this is our population variance. So you have to do a little bit of work on your calculator. Okay, a little bit. That's nothing too much. Okay, so that's how the calculations. We'll talk a little bit more about this in the second part of this lecture.